So it is my pleasure to introduce the second talk of this session, which will be given by K. Srinivas, Gaps Between Zeros of Epstein Zeta Functions. So please, Srini.
Thank you, Michelle. And I thank the organizers for such a wonderful event. Unfortunately, it is online. It would have been much nicer to have physical meeting in Chennai. And so my talk is gaps between zeros of Epstein zeta function. So this is a problem that I have been working for quite some time on the zeros. And there are some interesting developments that I would like to share with all of you. So before that, so the plan is I will first briefly describe what is the Epstein zeta function and some results that we know and how we got improvement over that, and then the recent work that is going on. All right, so that's roughly the plan of the lecture. All right, so let Qxy be a positive and definite integral quadratic form, and Rqn, the number of solutions of this equation, Qxy is equal to n. Then associated to this Q, one defines the Epstein zeta function as zeta Qs is summation 1 by Q xy to the power s, and one can write it as Rqn by n to the power s in the form of Dirichlet series. All right. And the analytical properties of this function, zeta function, is well known. For example, zeta function, this Epstein zeta function can be analytically continued to the entire complex plane, except for a pole at s is equal to 1, which is simple, and residue 2 pi by square root of delta. And we will denote delta by 4ac minus b square, which is, since it is positive definite, so delta will be bigger than 0 with this symbol. And it satisfies a nice functional equation of the Riemann zeta type, gamma s going to 1 minus s with these factors. All right. And we shall assume that delta is not a square, so that square root of delta is irrational. Other cases like delta is 4 and all these things, trivial cases, are either easier or well known. Now, h of square root of minus delta, let it be the number of inequivalent forms with discriminant minus delta. Okay. So there is a way of defining equivalence among the forms. So let h delta denote the class number. Okay. It is well known that there is a one-to-one correspondence between the equivalence classes of quadratic forms of discriminant minus delta and the ideal classes of the imaginary quadratic field. In fact, the Dedekind zeta function and the Epstein zeta function, they are related in this way. Okay. So where L denotes the number of units in the field K. Okay. Now, the Dedekind zeta function has an Euler product, and therefore one can reasonably expect a Riemann hypothesis. However, if the class number of these quadratic forms is bigger than 1, so in this talk I will only talk about positive definite integral quadratic forms. So when I say quadratic form, I mean this one. Okay? Then zeta Qs has no Euler product, and the Riemann hypothesis fails to hold for it. Okay? In fact, Davenport and Hellgren in 36, they had shown that if the class number is bigger than 1, then it has infinitely many zeros to the right of line 1. So S will always be sigma plus IT. So sigma is the real part of S. And Voronin in 76, in fact, he showed that in the critical strip between half and 1, there are at least t zeros in a box of height t. Chawla and Selberg, they showed the existence of a real zero between half and 1. And Bateman and Broswell, they improved it in this way, that if k is bigger than this, then there is a zero between half and 1. Stark, he proved that the existence of a number k, small k actually, this one, that if, if k is bigger than k, then all the zeros of this are simple. In this rectangle, they're simple with the exception of 2 real zeros between 0 and 1. He further gave a density, zero density estimate of this type. Okay. Therefore, though this Epstein zeta function has infinitely many zeros off the critical line, nevertheless, it has infinitely many zeros on the critical line, and that is our interest. Okay. So, in fact, the first result was by Porter and Titchmarsh in 1935, who showed that there is a zero half plus I gamma of this Epstein zeta function with gamma lying in t to t plus t to the power half plus epsilon. So we will call this as gap, this number, t to the power half, t to the power theta. Okay. So this was proved in 1935, and till 1995, this was the best known result. And Shankar Narayana, he managed to improve this result by removing this epsilon and replacing it with log. All right. And the next, so this was a barrier, like this half looked like a barrier, this exponent half. All right. So in 2005, Zutila and myself, we showed that, in fact, we can cross this half line to the left of half, and we managed to go up to 5/11. The moment we crossed half, we just left it there. Okay. And more recently, with Stephen Baer and Usha, we showed that, in fact, this 5/11 can be improved to 3/7. Okay. This is the recent result. This is for positive definite quadratic forms. And we are thinking about indefinite forms, but that seems to be very difficult. And in that case, still Shankar Narayan's result, this one, is the best one. All right. So in this talk, I would like to discuss how we got this improvement of how we crossed this half barrier, and then only talk a little bit about this recent development. That's the plan. So basic idea of the proof goes back to Hardy. Okay. In fact, all the proofs of showing infinitely many zeros for any well-behaving L function or a zeta function, most of the proofs, they depend on, the approach is by Hardy, which was simplified by Hardy and Littlewood, who showed that every interval of the type t to t plus h contains the ordinate of a zero of zeta half plus I gamma with h t to the power 1/4. In fact, this is a very elegant proof, very nice proof by Hardy and Littlewood. And all the proofs that I know of theorems on gaps or theorems or Hardy analogs of Hardy's theorem for other L functions, they somehow imbibe this. The basic approach is this one. Okay. So this is amenable for generalization and all these things. All right. So what is the starting point of Hardy and Littlewood? The starting point is, look at the functional equation and catch hold of this Hardy's function, WT. Okay. By functional equation, this f of half plus it is same of f of half minus it. Therefore, wt is real for real values of t. Okay, and also if you take absolute value of wt, this is same as absolute value of half plus f of half plus I. Therefore, the zeros of that and the zeros of this will come from zeros of zeta q of half plus I. Okay? Because the gamma functions will not have zeros. And therefore, in order to show the critical zeros of this zeta function, it's enough if one can show that wt, this function, has a real zeros, okay, for real values of t. So that is the basic point. And so therefore, assume that wt has no zeros in the interval t minus h to t plus h. Okay. With h, we will find what is h. Okay. This is the gap that we want to find. Okay. And take a smaller number, h naught, which is slightly smaller than h, and consider the integral I. This is on the half line. All right. So now, by our assumption that wt has no zeros in this interval, it follows that the mod of the integral as same as integral of the mod, because there is no change of sign. All right. And if this equality is violated, then it implies that there is some t in the interval t minus h to t plus h, for which the zeta function vanishes. That means there is a zero. There is an odd order zero. So this was the idea of Hardy and Wittlood. And so therefore, the entire thing is now how to show that the equality is violated. So if one can show, and then for what h one can show. Okay. So the contradiction is achieved by estimating the integral from above and below, provided h is 3/7. Okay. This is the recent Stefan and Usha's thing. All right. But we will describe about 5/11 first. So as it happens in most of the problems, when you want to show, one of the step is easy and the other step is very difficult. Okay. So here also one has to find an upper and lower bound for the integral I, mod I. Okay. So estimation from below, lower bound, is extremely easy thanks to a general result of K. Ramchandra on the mean lower bounds, first power mean lower bounds for a general Dirichlet series, which says that there are points where, if under certain conditions, the function cannot be too small. Right? And okay, and this was simplified by R. Balasubramaniam, and it is written in a more usable way, because the original theorem is pretty long and too complicated, and it's very difficult to guess that in fact this is what is being said. So luckily, like, Balu has managed to put it in a more human way, which has been very helpful for many mathematicians, because they can simply apply this one. So what it says, that you have a Dirichlet series Bn by n to the power s. Not all coefficients are 0, and suppose it has analytic continuation up to some number a, to the right of a, and there it has a polynomial growth. Then it says that for every epsilon, this is at least h. The integral is at least h. Okay, and the main point is h can be as small as log t a power of log t to the power epsilon. Okay. So for in showing the upper and lower bounds for the integral I, the lower bound is very easy, and as you can see that it is a very general. For you take any general dirichlet series, for example, a series which belongs to Selbert class, we know that it has a polynomial group, and you can apply it, and you can find the lower bound as bigger than h for any h bigger than a power of log t. However, it is the upper bound which is the difficult part, most difficult part. And as you saw before, Hardy and Littlewood, they could manage that the h is only about t to the power 1/4 plus epsilon. Of course, that was improved by, for zeta function, that was improved by Balsubramaniam to t to the power 1/6 plus epsilon, and Karatsuba to 5/12 plus epsilon, and so on and so forth. Okay. Yeah. So the hard part is finding an upper bound for the integral I. All right. So we start with this I. I is this integral, and then you see this zeta function half plus I t plus u. So there are two ways here. Either one moves the line of integration from half to 1 plus epsilon, like how Hardy and Littlewood they did it to get t to the power 1/4, and all other methods also. And Shankar Narayanan, he moved it to one line, and he could remove the log t part there. So either one can move the line of integration to the right, or one can stay on the line half and use some approximation to this zeta function. Okay. So therefore, this needs approximate functional equations, and here is the approximate formula for zeta half plus it, which was developed by Jutila for cusp-form L functions, and the same proof follows for our Epstein zeta function also. Okay. So here, look at the form of this one. Zeta half plus it is for any x, it's up to x plus x to 2x, this thing, plus these are the errors. Now, if you take x to be t to the power cube, you see that this is t to the power 3/2 by t square. So, and this is also, so both of them are of the order t to the power minus half plus epsilon. So these are the errors. Okay. Therefore, one substitutes this approximate formula into this integral that we have here, and then this takes this form, and this is the error. So here, the main thing is, in all of this business, there is a particular sum which gives problem, which becomes too big. Okay, and that in this case, the sum is around when t, small t is around t by 2 pi, with square root of delta. Okay, if you look at a Selbert class of functions, then one needs to do this kind of things for sums when n is close to t to the power d by 2. All right, a certain sum of this form. Okay. And if you can show that this particular sum is small, then you can get a good gap theorem. So here we extract this sum, this critical sum, and this k, what is this k? K and h are related by this thing, that k times h should be around t. This is the relation, okay, between k. So you want to show a gap of h, then you need to look at a gap, estimate this one, around capital T in an interval of length K, capital K. Okay. So the object is to show that this exponential sum is small. Okay. And the other terms, apart from this, all other terms can be shown to be very small. They don't contribute anything. They go to error because of Stirling's formula for gamma functions and all. Okay. And also complex integration. All right. So yeah. Therefore, our crucial sum, our integral I is this one, this one plus this one, second one, and crucial sum appears here in the blue color. All right. Now, rest of the things can be shown to be very small. Only thing one needs to consider is the one in the blue color. Okay. So therefore, the estimation of the sum S2. Okay. This is the S2. And so, yeah, rewrite that one in terms of this one. And then finally, we have T minus H to T plus H, gamma of half plus IT. RQ, this is the smoothing factor. Because this is 1 whenever n is around T by 2 pi at an interval of length K. Okay, so this is the sum we are looking at. Okay, and hence our S2 is H times supremum of T minus small t less than or equal to H, upper bound for this exponential sum. Okay, this Dirichlet polynomial. Okay, therefore we need to choose the parameter K as large as possible so that H can be made as small as we want. So the objective is to show that this sum is less than some T to the power minus epsilon, okay, whenever T and T are at a distance of H. Okay. Then combining with the previous estimates, finally, one can obtain H is equal to upper bound to be less than H naught times log T to the power minus 2. And remember, by using Ramchandra's theorem, we have a lower bound bigger than H naught. So that leads to a contradiction. Okay. That is the basic idea of the proof. And therefore, how to estimate this crucial sum? This sum I will keep calling as crucial sum or the sum in question. Okay, this is the we would like to discuss how to transform, how to estimate this so that we can make it small. Okay. So this sum is first transformed into another sum by using Voronoi formula. And that Voronoi summation formula is then transformed into another by using saddle point method. Okay. So this is the basic thing. And the Voronoi formula in question involves an additive character related to a rational number. And a rational number, suitable rational number is chosen among the convergence of the continued fractions of the quadratic irrational 1 by square root of delta. And this is because quadratic irrational, the continued fraction is periodic, which allows to control the denominators of the partial quotients. Because the partial quotients are bounded. All right. So I would like to explain a little bit about the summation and the transformation formulas that we have. So note that whenever we want to estimate sums of the form Bn, Gn, and e to the power 2 pi I Fn, where Bn's are arithmetical functions, Gn's are complex valued, and Fn's are real valued in some interval. Okay. So if f dash of x is close to a rational number, h over k, then this sum in 12 and sum in 14 are of the comparable. Okay, they're of the same size. The difference is very small. Okay. Therefore, this sum can be replaced, 13 can be replaced with 14. Now, if a summation formula for this sum 15 is known, then we can sum 13 by partial summation by parts. Okay. Partial summation. Okay. This is a standard thing. So in our case, we have our Bn's as Rqn, Gn as n to the power minus half, Fn as minus t by 2 pi log n, and therefore we look at the sum Rqn n to the power minus half, e to the power minus t by 2 pi, e to the power 2 pi I times this one, okay, minus t by 2 pi log. Okay. So this is what I was saying, that once we have a sum for this one, then one can sum this one by partial summation by parts. All right. And Utila has obtained this Voronoi summation formula for Rqn with the additive character Ekn by h. Okay. And so this is of this form. So yes, so this Voronoi summation formulas are available for when these coefficients are Kuss-Formel functions and quadratic forms, and I think mass forms by Moidman, I suppose, and very few other things. So one invokes this sum formula into this summation. All right. So one gets, so this is the summation formula. Now this is the starting point. Once we have a summation formula, okay, so then we get, in our case, we get Rqn, Ek, Nf, Fn to be of this form, okay, where J0 is a Bessel function. Okay. So this summation formula serves as a starting point for the derivation of a transformation formula for exponential sums. So the exponential sums in questions are transformed now by using this summation formula. So which means, okay. Now instead of applying directly this sum S, it is advisable to use a smoothing version of this. Okay. Namely 1 by u, 0 to u, SU t, where SU is this. Okay. Now, the difference between S and S prime is not big, so they're small. Now you can write SU as this sum by removing a factor MR and then multiplying e to the power MR. This has a lot of advantages. So therefore, now the summation formula appears as Rqn EMR times GM EFM minus. Okay, this is the Fn in the summation formula, and therefore, when we use the summation formula, the previous slide, we get this. All right. Now, this is the exact transformation formula, which is a little complicated with various things floating around. So the actual summation formula that in question is this one, and this is what is transformed into sums of this type, n less than or equal to nj. Okay. We have only two, N1 and N2 here. And all right, these are error terms, this go into error. And phi of x is like square root of x. So you see, this sum is transformed into another sum containing E of n, and then here exponential of phi of n, and phi is like square root of phi of n is like square root of n. So this n is nothing but the number of ways of writing qxy as n. All right. So here is a transformation into an exponential, double exponential sum, okay, involving x and y. So the various choices of these parameters are as follows. The k is, to begin with, we choose k, and then later we will maximize k. And this m1 and m2 are small, close to t by square root of t by 2 pi. And the convergent r is chosen in this way. So with this choice, the crucial sum is transformed, is estimated. It gives k to the power 1 by 4, n to the power minus 1 by 4, t to the power minus half times this exponential sum, double exponential sum. All right. And now we have two variables, x and y. What we did is we used Wander-Corput's method in one variable to estimate this sum, and in the other variable we took trivial estimate. And to our surprise, we could see that in fact the sum is small, and we can take h to be, we can take k to be t to the power 6 over 11, and that gave us h to be 5 over 11. All right. So you see, if you take a trivial estimate of where is the crucial sum? If you take a trivial estimate of the crucial sum, let me get that. Yeah. I should have written separately. Give me 1 second. Yeah. So if you take a trivial estimate of this sum, then this is around, the n is around t by 2 pi at a distance of k. So the length of the interval is k, and our n is around capital T. So n to the power minus half is t to the power minus half. Okay. And if we want to make it as small, t to the power minus epsilon, okay, then our choice of k is less than t to the power half, which makes our h to be bigger than t to the power half. Okay. So the earlier results, this was the barrier. So estimating it trivially, one would get t to the power half plus epsilon, the earlier bound. Okay. And therefore it required a sophisticated way of handling things, which luckily Jutila has done it for earlier in the TIFR lecture notes. He has developed this transformation, summation formula and transformation formulas, which has helped him to estimate the bounds for cusp form L functions, okay, an by n to the power half plus it. I mean, in fact, this if f is a cusp form, it allowed him to show that this is less than t to the power 1/3 plus epsilon. Okay. So this is where the main idea lied, but that was for the cusp form L functions. So we tried to work out everything for this Epstein zeta function. The cusp form L functions are entire functions, okay? But here we have a pole at s is equal to 1, and therefore it required to judiciously choose the parameters and see that everything works, and also the summation formula and transformation formula were developed here in this paper. All right. So this is, so we get a saving, and therefore we could show that we can cross t to the power half plus epsilon to half minus epsilon. Right. Now, yeah, so I was here. So this was the choice of parameters. And so, as I said, only in one variable, y range, we evaluated non-trivially using the summation formula and then Wander-Corpus form. Now, in the recent work with Stephen Baer and Usha Sangle, we have tried to estimate the critical sum non-trivially in the other parameter also. Okay. So we carried out the Weyl shift followed by B process, and then exploit the summation over X using Wander-Corpus bound. In the earlier paper, only Y range was non-trivially estimated, but here, by rearranging the sum, we have managed to also use Wander-Corpus estimate in the X variable, and this allowed us, this showed that, so therefore, in order to show that crucial sum is O of t to the power minus epsilon, was enough for us now to take k is to be t to the power 4/7 minus epsilon, and therefore we could obtain the gap to be t to the power 3/7 plus epsilon. So this is the recent result, and these are the things that we have used. This is a Weyl differencing. So this rearranges the sum in a more amenable way. And then the B process, we have used the B process. So the Weyl shift, it affects it reduces the original sum to a more tamely oscillating one, of course at the cost of loss of some accuracy, but we have managed to do that. And then the Wander-Corpus lemma, this is the one we have used in the other parameter. So then the final estimate comes out to be, this was there before, and then we managed to save something more, and finally we got k to the power 7/8 by t to the power half log t plus t to the power k to the power 17 by 8 and t to the power 3 by 2, which is O of t to the power minus epsilon, provided k is about t to the power 4/7. So k is t to the power 4/7 means h is t to the power 3/7, because h times k is about t. All right. And now the other details are very technical, so I don't want to discuss. I didn't want to discuss those things. This is there in our paper in functional approximatio. Okay. And all the details are there in the both papers and the references of this paper, where Jutila's development of exponential sums related to quadratic forms is there. And since this is the last day of the talk and such a long conference, people must be tired also. I didn't want to make too technical and giving too technical details. So I would like to stop it here by thanking all of you. And I wish Balu a happy birthday. He has been extremely helpful in my career. And I wish him a long and healthy life. Thank you very much. I stop it here.
Thank you very much, Srini. Very interesting. You see, in my experience, when we have an integral, most often what is difficult is to give a lower bound, and what is easier is to give an upper bound. But I see that here, thanks to this lemma of Ramachandra, it is quite the opposite.
Yes, indeed. That's a very beautiful theorem.
Do you expect that the lemma of Ramachandra is optimal?
Sorry?
Do you expect that this lemma of Ramachandra is best possible?
I mean, this is best possible is I don't know, but this is the best one can expect, because
yes.
We would like to show that there are infinitely many points where the function cannot take small values. All right.
Yeah.
So
yes.
There is a well-spaced points between t to t plus h where the function is large, and that's enough. Because on the other hand, uniformly we have shown that the function, the values taken by the function are small. So that leads to contradiction.
Okay, thank you very much. Are there some questions from the participants?
Yeah,
Professor
question.
Yeah, Professor Walschmidt.
Yes.
I mean, suppose you are to the right of 1 for zeta function. This is definitely best possible. Even to the right of half, probably you can save a log t power 1/4. But to the left of half, for example, for zeta function, this can be definitely improved.
Okay.
Nice.
Okay. Thank you for the comment. Thank you, Balu. And so, any further comment or question?
Stefan.
Yeah.
Yes.
So thank you very much for the nice talk. So I remember we wanted to look at the indefinite case too.
You're right.
Maybe you can say something about difficulty.
Yeah. So the problem is, as I said, for the indefinite case, it was the Hardy's theorem was proved by K. Chandrasekharan and Raghavan Narasimhan. Okay, and then their proof also gives half plus epsilon, and the epsilon was removed by Shankar Narayana. So Shankar Narayana's result is still the best known for the positive definite. In our case, we were looking at Voronoi summation formula, and also the problem becomes, because now this RQNs, the bound, the summation for RQNs, they give trouble because of existence of units and things like that. So we need to, because now the curve is unbounded. So we have to restrict it into certain, regions and then do it. So there is a possibility of doing it, which we will explore. So there is a hope that we will be able to do it for.
Yes.
Yeah. And Jutila also expressed positive hope that it can be done.
Yeah, let's look at it.
We shall. So let formula subside a little bit.
Mm-hmm. Okay, thank you very much.
Thank you.
Mm-hmm.
Okay, thank you.
Sir.
Any further question or comment?
Yes, I have a question. So, sir, if you consider any NRE positive definite quadratic form and consider corresponding Epstein zeta function, so where is the actual difficulty arise to if you going through your method? You
the
mentioned
difficulty. See, as I said, the difficulty when you represent it as an integral, you see that you have then e to the power 2 pi I times f of the function of n and t. All right.
Yes.
In the integral. Now, when you take the derivative, the saddle point, catch hold of the saddle point. The problem comes precisely around the saddle point. All right. So if you are able to show that the sum is small in a neighborhood of the saddle point, then you are done. So here, as I said, t to the power in a degree d case, you have to estimate the sum closer to t to the power d by 2 in a small interval of length of around t to the power d by 2. Other things you can do quite easily by the method that I described.
Okay. So this lemma by Zutila, this is also true for general case also?
Wherever you have Voronoi summation formula, you can use this one.
Okay. Okay. Yes. Okay. Thank you.
And we have a result for Selberg class up to degree less than 4 under certain assumptions. You can look at Krishna Rajan's thesis. There's a chapter in that. So that will give you where is the trouble, where is the actual crucial sum that comes.
Okay.
Exactly. This Hardy and Littlewood's idea.
I see. Okay. Thank you.
So thank you for this answer, Srini. Any further comment or question?
Yeah, I have a question, if I may ask.
Yes.
So can you consider same thing for, from your method for the linear combination of this function? Because in the beginning, as you mentioned, the Dedekind zeta function can be expressed as linear combination of function.
You can also look at the linear combination. As I said, for it is possible, provided you have functional equation. Of course, you have. I mean, if all the functions have the same functional equation, then you have a linear combination. You can do it for linear combination.
So are you saying that doing for the linear combination will give same estimate for Dedekind zeta functions? I mean, from in one slide.
See, for Dedekind zeta function, or you are talking about comparing Dedekind zeta function and the partial zeta function.
Yeah, so there was a slide in the beginning, right, where you expressed Dedekind zeta.
I mean,
sums of Epstein zeta function. So I'm wondering that if basically having estimate for the linear combinations, so can we obtain the similar result for Dedekind zeta functions?
Yeah, I mean, you are showing see, this method will give you the zeros of each of this partial zeta functions, right?
Mm-hmm.
And therefore, combining them, you can say that the Dedekind zeta function also. For example, if the class number is 1, let's say, then the Dedekind zeta function is the Riemann zeta function times a L function of a quadratic character. In this case, trivially it follows. But if you have a linear combination, then also it will give you information. Balu, I think I'm saying correctly, right?
Yeah, I think it should follow. Although like showing the sign change of the linear combination, sometimes it's a little bit more tricky. As you know, the Selberg conjecture for B12 function for linear combination, it's like.
In fact, Bombier and Hazal, they have looked at linear combination of L functions which satisfy a certain type of functional equation, and they talked about the zeros of this linear combination.
Sudhir, suppose you start with a linear combination, how do you construct a real function out of it?
That's why there's some conditions are required so that they should have.
The whole Hardy's method is first of all by getting a certain real function.
Yeah, so there are, I think, two ways in our recent paper with Mithun. So one criteria we have given even for complex linear combination under certain restrictions. And the other way is you look at the individual Hardy G function, all of them are real. And you look at their sum.
Okay, I see.
Yeah, under some conditions.
Other way also where we have given in a recent paper with Mithun Kumar Das, a complex linear combination also we have generalized how to make it real under certain restrictions.
Yeah, then
In
you
fact-
should work.
Yeah. In fact, in our paper also you have seen, Sudhir.
Maybe in the linear combination, if you have some common Euler factor, then possibly Karatsev has some result.
No, Euler factors you will not have, you see.
No, some
partial
common
zeta
factor.
function.
Some common factor.
But if they satisfy the same type of functional equation, then it is possible that the linear combination, you can write the zeta function, Hardy's zeta function. It is there in Bombier and Resnal's paper.
Yeah, if the gamma functions are the same, then of course you will get a same functional equation for everything, right? So then there's no problem.
Right.
But that's a pretty rare event and certainly not going to happen in your case, I think.
Yeah, we look at individual L functions.
So thank you very much. There was a very interesting discussion. So it was very good, Srini, that you left enough time for this discussion. And so I thank you again. And I close this second talk. And then we meet in 7 minutes for the third talk of this morning. Thank you very much.